everybody and welcome back to my channel. So a few days back I uploaded a video on heaps where I mentioned about building a heap in just order of n, which is linear time. So in this video I will be explaining how we can build a heap in order of n. Now for all those people who see my videos, like my videos, but they do not subscribe to my channel, so please don't do that and just click that subscribe button. Now let's see how we can build a heap in order of n. Now before going to the main part, let's first see some main points which you should know in order to prove mathematically that how we can build our heap in order of n. Now first of all, if I have a binary tree with n number of nodes, and with L levels, so there are some points which are to be remembered. First of all, total number of internal nodes are n by 2 approximately, and the number of leaf nodes are n by 2. So over here, the leaf, now first let's see what is a leaf node. Leaf node is a node which has no child node or zero children node, and internal nodes are the nodes which have at least one child node. So over here, these are my internal nodes and these are my leaf nodes. So approximately there are total number of the half of the nodes in a binary tree are the internal nodes and half of them are our leaf nodes. Now let's see how. Now over here we can see that we have just one node. In the second level we have 2 nodes. In the third level we have 4 nodes, and in the fourth level we have 8 nodes. Now this is to the power 0, this is 2 to the power 1, this is 2 to the power 2, and this is 2 to the power 3. Now using this we can simply derive a simple thing that in level L we have 2 to the power L minus 1 number of nodes, which is our fourth point. That for every level L, the number of nodes in that, or the maximum number of nodes in that particular level is 2 to the power L minus 1. Now if I want to calculate the total number of nodes, we are just going to take the sum of this, and this we will have a GP series. So we will be having a sum from 1, then 2 to the power 1 and so on up till to the power L minus 1. And this one is nothing but 2 to the power 0. So this is our GP series, and the formula for the summation will be 1 2 to the power L minus 1 upon 2 minus 1. Now this I have written using the formula for the GP series with the common ratio greater than 1 and our finite GP series. So using this we simply get the total number of nodes in a binary tree with the level L are 2 to the power L minus 1. These are the maximum number of nodes that a binary tree with L levels can have. So this is a point 3. Now the main point, because of which I have told all of this to you, is the point 5, which will be directly used in the proof for that, which will be used in order to prove that we can build a heap in order of n only. Now over here that I have written is that the contribution of nodes on height h in the total number of nodes is of n by 2 to the power h plus 1. Now what is height? Now over here we say that the leaf nodes are of height 0 because there are no nodes below that. There are no edges below these nodes. Now coming to this, over here we have one edge below these nodes. So these are at height 1. And these are at height 2 and these are at height 3. Now using this we can simply see that we know that in the last node or in the last level we have our leaf nodes, and the leaf nodes are of about 2 to the power n by 2 approximately. Now these are n by 2 because as we know that we have 2 to the power L minus 1 total number of nodes, and in the last level we have 2 to the power L minus 1 number of nodes. These are the maximum nodes I am talking about. So using this we can tell that the internal nodes are this value minus this value. So over here we can write 2 to the power L as 2 to the power 2 into 2 to the power L minus 1 minus 1. These are the total number of nodes minus the number of leaf nodes, which are 2 to the power L minus 1. Now if I just subtract this from this, so I get 2 to the power L minus 1 minus 1. And we can see over here these are the number of leaf nodes and these are the number of internal nodes. So they are approximately same. So we have approximately to the power 2 by n by, so we have approximately n by 2 internal nodes and n by 2 leaf nodes. Now if I see for this part, now over here let's see how many nodes are contributed by these nodes, like how many total number of nodes or what percentage of nodes is being contributed by this level. So over here we know that every level has half the number of nodes than its next level. I'll repeat it again. The number of nodes in a particular level are half the number of nodes in the next level, and this is only when I'm talking about a complete binary tree. So over here I can see is I have only one node over here. So over here I'll have maximum 2 nodes. Over here I have maximum 4 and over here I'll have maximum 8 nodes. So now if I use this, now over here we have 2 to the power h plus 1. Now we know that this is at height 0. So if I place 0 over here, so I'll have 2 to the power 1, which is n by 2. Now let's talk about height 1. Now over here height is 1. So I'll place 1 over here. So I'll have n by 4, which is 2 to the power 2. Now let's see if this is true or not. See, over here I had 1, 2, 3, 4, 5, 6, 7. 7 plus 8, 15 nodes. And in this level I had only 4 nodes. So this is approximately 4 times, which is this level or this height has contributed n by 4 number of nodes in the total number of, if the total number of nodes in the binary tree is n. Similarly for the rest of the levels. Now let's see how we are going to use this in order to prove that our build heap method works linearly, that is in order of n. Now let me just give you a quick overview how the build heap method works. Over here we know that we just take these leaf nodes as the nodes which are already satisfying the conditions for a heap. Let's assume I'll be building a min heap over here. So we'll assume that these are already correct and these just satisfy all the conditions. Now we are going to check for the internal nodes. We are going to check for internal nodes and we are going to simply perform the down heapify method on these nodes. Now as we are going to perform down heapify method on these nodes, on n by 2 number of nodes, the down heapify method as requires log n time, the time complexity will be of order of n log n. But this is true, but this is not asymptotically tight. This is not a wrong answer, but this is not asymptotically tight. Now what this means is, order of n log n means that it will take maximum time of n log n. So if I even write this as order of n square, it is correct because it won't take time more than the order of n square, but it is not asymptotically tight. Asymptotically tight means that that is the time which we expect it to be. So let's see what is the asymptotically tight bound for the time complexity for building a heap. Now over here we know that a heapify method travels the height, and we know that the height, the minimum and the maximum height that it can travel is from 0 to edge. 0 height will be traveled when the node is already in the correct position, and maximum is of h, which will be traveled when the root node has to be brought to the leaf node. So this is the range, and the height of the binary tree over here is of log n. This is just a floor value in order to get the correct answer. Now let's see how we use these things in order to derive our that it works in order of n. Now see, the total number of nodes that are to be subjected under the heapify method are n by 2 to the power h plus 1, where our height can go from h is equals to 0 to h is equals to log n. Now over here I won't be writing the floor or the seal symbol over here because it won't affect that much. Now these nodes are to be travelled at max of order of h, which is the height of my tree, and this is done by the heapify method. Now over here we can see that n is a constant, so we can just simply write it as order of n, then summation h is equals to 0 to log n h upon 2 to the power h plus 1. Now all we have to do is we have to just find the value of the summation. Now if I expand the summation and I write it, so we'll have that this summation s will be equals to, when I put 0, it will be 0 plus 1 by 2 to the power 2 plus 2 by 2 to the power 3 plus 3 by 2 to the power 4, and this will be done up till log n, which is log n by 2 to the power log n plus 1. Now see, this is an AGP series. Now if this would have been a GP series, we could have simply got the sum. But because of these, that is the arithmetic part over here, we cannot directly calculate the sum. So we'll just simply multiply the common ratio with it. So we'll have 1 by 2s, because over here the common ratio is 1 by 2. Now just see carefully how I will reduce or just convert these numerators into 1. So over here half into 0 will be 0. Now half into this particular is 1 upon 2 to the power 3. Then we'll multiply half by this. So I'll have 2 upon 2 to the power 4. Now over here I'll have log n minus 1, which is I'm multiplying the number previous to this term by 1 upon 2. So over here I'll have log n plus 1. Now the last term will be log n upon 2 to the power log n plus 2. Now if I just subtract these two equations, so what I'll have is, over here I'll have half s, which is equivalent to, this minus 0 will be the number itself. Now over here, well, I'll subtract these two, so I'll get 2 to the power 3 with 1 as my numerator. Now when I'll subtract these two, I'll get 1 upon 2 to the power 4, and then up till this term we'll have 1 upon 2 to the power log n plus 1, and the last term will be log n upon 2 to the power log n plus 2. Now over here we can see that this part is an GP series, a simple GP series, and only this part has to be taken care of. Now using the formula for the summation of the GP series, we'll get 1 upon 2 to the power 2, which is the first term, then 1 minus 1 upon 2 to the power log n, which are the total number of terms in my GP series, and this whole will be divided by 1 minus 1 by 2. So over here, this 1 by 2 will cancel one of the 1 by 2's over here, and this will be 1 upon 2 to the power log n, and this can be written as half into 1 minus 1 upon 2 to the power log n. Now we know that this log n is of base 2 because as it is a binary tree, so the base is of 2. So when this base and these two are same, so these just cancel out. So we get 1 upon 2, 1 minus 1 upon n to the power of log 2 base 2, because these both can be simply swapped and log to the base 2 is 1. So this is, so now over here the value that we get for half s is equals to 1 by 2 into 1 minus 1 by n plus this last term, which is plus log n by, now see over here 2 to the power 2 can be written as 4 into 2 to the power log n. I'll just write ln. Now we know that this is of base 2, so even this will become n. So over here we'll have this term. Now the time complexity that we were looking for was order of n into this summation s. So this half gets cancelled out over here. This becomes 2. So now we have n into 1 minus 1 by n, and this term plus log n by n, 2n. So now when we open this up, we get n minus 1 plus log n by 2. And when we take the big O of this thing, so the one with the highest degree is n, because this is constant and this is logarithmic time, which is less than the linear time. So over here we can see that order of n has come, and this is more tighter than n log n. So this was all for today's video. In case if you find my video informative, do share it across with your friends. And I upload short notes on my Instagram account. I leave the link in the description box. And you can follow me on my GitHub and my LinkedIn as well. Do subscribe to my channel and hit the bell button. Thank you.